When we wrapped up with this first part of Prandtl mixing and the law of the wall to derive a real rigorous boundary layer equation for fluid flow, we were discussing how eddies moved parcels of mass up and down through the flow and how that actually caused then momentum to be mixed, with some slow material from near the bottom of the flow being moved upwards and some fast material from near the top of the flow being moved downwards. And I mentioned that now that we have a definition for K, this what we so-called eddy viscosity, what we can do is insert that into our constitutive equation and use it to be able to solve the relationship between stress and strain, or rather stress and velocity gradient, because it's the vertical velocity gradient that is the fluid response to the shear stress. There is one problem, though, is that we have this L term, and this L is the size of the eddy. And right now, although this is about to change, we don't have any way to a priori say what the size of that eddy should be. And should it be, gigantic? Should it be, like kilometers, long? Should it just be, a teeny tiny micron scale, just barely above the smallest possible length at which an eddy can exist? Eddy, what size should it be? And that's important for determining the relationship between stress and strain. As a matter of fact, it's squared important, right? So anything that affects the eddy length ends up greatly impacting the result of this equation because that value is squared. So this is where we take advantage of the fact that we're near the boundary of a flow. And near the boundary of the flow, we can say that L, this eddy length scale, is approximately the same as Z, the elevation above the bed. And we can say that for two reasons. The first one is because the scale of the largest eddy is always equal to the height above the boundary. And that is hopefully not so difficult to see. So if we have a bed right here, and we have a water surface up here, the largest eddy that can exist in that water is simply bounded by the distance. Oops, that's not quite the largest eddy, is it? Selling it short. All right, let's go. All right, that's much closer. The arrow touches it at least. All right, so the largest eddy, L, is going to be equal to Z, because nothing bigger can exist within the flow because the flow just isn't big enough to hold it. It's a very simple geometrical argument. In fact, I'm just going to write that down right there. The second reason is because within these large eddies, there are smaller eddies which can be whisked along, but then those actually are just carried within the bigger eddy and are mixing fluid within it. So if we have an eddy that's bringing fluid from way down below up here, we might have within it some sort of, other smaller eddy like that. But that eddy is just mixing material within that bigger eddy, and overall, those smaller eddies, if they exist, in multiple directions, might end up just homogenizing what's inside the biggest eddy. And so the biggest eddy ends up being the most important eddy for determining the mixing of fluid parcels from down low in the flow to the middle of the flow to up high in the flow, and then perhaps back down in the flow. So rivers are shallow enough that the flow resistance posed by the bed affects the full velocity profile, and this makes them different than the atmosphere. So we talked a little bit last time about the fact that this equation could also be used for the atmospheric boundary layer. But above the boundary layer that's affected by things like buildings and tall trees and mountains and so forth, there is a layer of air that is moving at essentially a constant velocity. And that just doesn't exist at least in any river that I know of. In all rivers that I know, this law of the wall, while not rigorously true for the entire velocity profile all the time is actually a very successful approximation to the flow, and we don't really see some kind of like free streaming constant velocity region within a river. So, therefore, because we can assume that this whole region is within this sort of boundary layer, just writing boundary layer flow, so we know, then we can say that for the entire river depth, we have L squared replaced by this Z squared, or Z squared. Wow, I'm starting to sound like a Canadian. So, here we are. So I just wanted to do another little drawing. It's basically the same thing I drew over there on the margin, but let's make it a little bit bigger, where we have the bed of the channel down here, and then we have the free water surface at the top. I'm just going to mix the colors up a little bit. And then within here, we might have some, eddies at the bottom of the flow. We might have some eddies at the top of the flow. And we might have some really large eddies going all the way from the bottom to the top. And so you can imagine, and I'm going to use this lighter blue to show like these parcels of water again that are being moved up. And so this one is going to be taking a slow parcel up. And then if there's a parcel like this that's fast, that's going to be bringing that back down, and again, homogenizing this velocity profile. That's our expectation. And so all of these are mixing fluid in the vertical. And one thing to note is that there are horizontal components of the motion of these eddies, right? But if we just have varying velocity with depth, it doesn't matter if flow is moving left to right. It only matters if that flow is moving up and down. So equation 35 gives us this nice expression that we can insert into equation 30. So let's go back up here. So we have So we have this tau equals k du dz. So let's go ahead and write that. Tau equals k du over dz. K equals, too far up, this kappa squared, so von Karman's constant squared. And remember, I told you earlier that we are squaring von Karman's constant as a matter purely of convenience, and that convenience is about to be realized. Density elevation squared above the bed, where that elevation above the bed again is this L, this length scale, this diameter of the eddies, du dz. So we have kappa squared rho z squared du dz. And so from that then we can see that we just, once we plug that in, we get all of our same terms except there are two du dz's, and they're multiplied together. So this is not d dz of du dz, which would produce a diffusion equation by having a differential operator. Well, except for the fact that this, if the differential operator were applied to this as opposed to just somehow being multiplied by it. But rather, this is another du dz, so we have du dz at quantity squared. Then we have z squared, kappa squared, and this little rho hanging out by itself. So tau b and rho are the only two terms that are not squared. Well, we're getting to the point where we talk about this thing called shear velocity, which I mentioned earlier, that shear velocity is related to turbulent intensity. And I told you that it was related to turbulent intensity purely by analog, by showing a video in the lecture notes and also mentioning here in the class that if there is more shear in a flow, there is more force available to push one layer along above another. Kind of, you can imagine like rolling a tire with your hand. You hit your hand across the top of it, and the tire rolls. That's shear. And so that shear creates turbulence. It creates spinning motions, just like that spinning wheel in this solid state analogy. So I mentioned it that way, but I actually didn't tell you why it existed in the first place. And so this is something that Prandtl came up with as a result of producing the law of the wall and building this analysis of the velocity profile. So he wanted to solve this and realized that you could take tau b over rho, and the square root of that is in fact a velocity scale, which he then said is the shear velocity, so the velocity driving turbulence. So I want to write that here. So shear velocity equals, by definition, the velocity driving turbulence. And I just want to reiterate that this is not a velocity that is like how fast the flow is going on average. No, that's u bar. This is really, you can think of this as a velocity scale, or a term that has the units of velocity, but it is acting in a way to speed the eddies through the flow. And so the scaling, just really relates to the fact that, the shear stress is all about the near wall gradient in velocity. Right, so if we're thinking about the tau b, the shear stress on the bed, that is related to the velocity gradient at the wall, and so therefore if there's higher velocities in the channel, those will produce a higher shear stress at the wall, because then there's a bigger gradient between the channel flow and the zero flow at the no-slip boundary. So, using this equation here, 36, let's solve for shear velocity. So, first off, I just want to back up and say, why are we solving for shear velocity, other than the fact that, those of you who are, a little quicker with math might realize that it's going to very nicely lump the terms. Well, the mathematical convenience is indeed one reason, and the other reason is that we have other expressions to, define what the shear stress and the shear velocity should be. So, for example, you might remember from the depth-slope product, we can define shear velocity in terms of the slope of the channel, gravitational acceleration, and the density of the fluid. And so, therefore, if we solve for shear velocity, we have a way to connect this driving stress with deformation within the flow, and eventually link it back to the fluid velocity profile. So we can see how the forces driving the flow produce a profile of velocities throughout the fluid. So here we go. So we just have this thing right here. Let me just show you how that happened. So we have u tau is equal to the square root of tau b over rho. So up here, tau b equals, I'm going to pull the rho out here, rho kappa squared z squared du d, got it, getting it backwards, dz squared. Now, if we move rho over here, we can divide through by rho, and then we know that u tau is equal to tau b over rho to the 1/2 power. It's a square root. And so if we look at this 1/2 power, if we take the square root of this side, this turns into u tau, but then we have to take the square root of the other side too. And so that means that we end up getting equal kappa z du over dz. And that is indeed exactly what this equation shows. So, now let's look at this. From u tau here, we can get this from the driving stress on the fluid. Such as through the depth-slope product. Kappa is a constant, so we're all set there. Z is just the elevation within the flow. That's great. And U is what we actually want. Velocity. All right, yay. So let's think about then how to rearrange this to be able to give us a velocity profile. And so the first thing I do is just rearrange the equation to have du dz be all on the left-hand side. And as a result, we have u tau right there over kappa at the bottom, and then we have 1 over z, and I've left the z separate because it's one of the terms in the derivative, and so that's going to become important when we try to integrate it. And so what this is showing right now is how momentum mixes vertically through eddies and how that creates this velocity profile. So if we want to then be able to visualize what the velocity u as a function of elevation z is, let's get started. So while there is not a differential equations class that's required as a prerequisite for this class, a technique in solving differential equations that's so laughably simple that I don't know if they even teach it. I think I remember doing it maybe on the first day of my own class. It is one way of solving equations, and that is called separation of variables. And so we have this du dz on the left-hand side, but let's think about how we can rearrange this to turn this into something we can integrate on both sides. And so we have to keep the variables that are being integrated over consistent across both sides of the equation. And what I'll do for starters is say du equals u tau over kappa dz over z. And so now I have all the u's on this side and all the z's on this side. Then the next step that I can do is integrate. And so on the left-hand side, that's really easy. Integral of du is equal to u tau over kappa. And u tau, we're going to say that the driving stress is not a function of z, because this is the shear velocity that's related to the basal shear stress, just at one point in the flow. So not function of z, so that does not go inside the integral. And kappa is just a constant. So then we can just put the integral over here and keep those out of it. Ooh, that was an ugly integral. That's a short integral. That's a nicer integral. There we are. So dz over z. And so for some of you who might be trying to scratch your heads and remember, how do you actually solve this integral? Well, let's go to this one first. Integral of du is just u plus a constant of integration. We'll call it u right there, and we'll add in the constant from this integral over here. Because if we have plus a constant on the left and plus an arbitrary constant on the right, we put those two constants together and it's just another arbitrary constant. It doesn't matter. So we can just have one arbitrary constant in this equation. So we have u equals u tau over kappa times something else. And the way I like to remember this one is that, remembering what dz over z is a little difficult, and sometimes people do u substitution, but we already have something with u. So I'm going to do this thing called cabin substitution, and I'm going to say that we have the integral here of 1 over cabin d cabin. Great. And so you might ask yourselves, all right, well, what's the integral of 1 over cabin d cabin? And that, my friends, is log cabin, but because it's made of natural logs. It is a natural log cabin. Here's a little door. So ln cabin plus c naught, some constant of integration. And we'll just substitute the d back in, or the z back in, to go like that. So this equals u tau over kappa ln of z plus c naught. And you might say, hey, wait a minute. The c naught was multiplied by u tau over kappa. Well, sure, but this is just an arbitrary constant that could be anything. This is an arbitrary value, this is an arbitrary value, so it doesn't matter again. We can multiply it, we can not multiply it, but it will end up just being some value that comes out when we start to evaluate along the boundary conditions. And that's the next thing that we're going to do. So in order to try to figure out what c naught is, we have to decide what u is, some point at which u is going to be some known value, and then we can solve for c at a known z and a known u. And this is where we're going to talk about the difference between a real flow and our idealized flow. So in a real flow, as you get really close to the bed, so we're going to have the surface of the flow up here, and we're going to look with our little magnifying glass at the zone that's really close, just sitting in right here. And if we have this zone, this near bed area, what we're going to see is that there's a zone at which we go from having this sort of this logarithmic velocity profile. I'm actually giving away the answer, but I don't think that that's quite so giving away as it would have been if I'd given that a little bit sooner. And so there's this logarithmic velocity profile, and at some point it goes into becoming a linear velocity profile again, just like this linear viscous fluid. So just like this plate that you had in the prior example, this cutting board shearing the peanut butter. And the reason here is because the Reynolds number, which controls whether it's viscous or laminar, the Reynolds number is equal to velocity times length over nu. And as elevation goes to small, velocity goes to small, and elevation is going to be the length term. So what that means is both the terms in the numerator become small, and at some point we switch over to laminar flow. So this is called the laminar sub layer. And it can be important in some ways in real flows. So for example, if we have a bunch of rocks down here in the laminar sub layer, the flow resistance might be affected by a flow path that's bouncing around like that. And that's actually kind of hugging those individual grains. However, in most natural rivers, we don't care so much about that. This is called hydraulically smooth flow. Most natural rivers are hydraulically rough. And on top of that, this is a teeny tiny zone at the very base of the stream, and we're trying to figure out what's happening with the velocities through the bulk of the stream. And so we'd like to not think about the laminar sublayer. The laminar sublayer, again, is very important for benthic biota. A lot of small animals will live in the laminar sublayer and then reach their little feeding tendrils up into the turbulent mix zone to sample whatever's floating by and then retreat into their safe little laminar sublayer again. Ecologists care a lot about it, but right now I'm going to tell you that it exists, and then we're immediately going to slam the door and ignore it and say that, well, from this we're just going to approximate that at some point above the base of the flow, we're just going to say that there is some point at which the velocity equals 0 at some elevation z equals z naught. We like to put knots behind numbers or after numbers if we're meaning that it's a specific level. This, despite the way I drew it, is kind of extrapolating here. Z naught has really no explicit physical meaning, but it is related to the roughness on the bed. All right, so if we take that, now let's move back over to solving this equation. So I'm going to plug in 0 for velocity equals u tau over kappa ln z naught plus c naught. Well, you can see pretty clearly that all I have to do is move this whole chunk of stuff over to the left-hand side of the equation to get c naught equals minus u tau over kappa ln z naught. Scrolling down. So then when we rebuild the equation all together, what we get is u equals u tau over kappa ln times the quantity ln of z minus ln of z naught. And this is where we're going to take advantage of this lovely thing called the Rule of Logarithms, or one of the rules of logarithms. And what that is the fact that if we subtract these two quantities together, this is the same as the natural log of the quantity z over z naught. And from this, we get the law of the wall, in which I say u and I'm going to write u of z. So velocity as a function of elevation above the bed is equal to u tau over kappa. So the force is driving turbulence divided by this coefficient that's relating shear to turbulent intensity times the natural log of the elevation above the bed divided by some roughness length scale. And therefore, the flow velocity is going to be a logarithmic function of the elevation above the bed, and is going to look something like this. So if this is velocity, and this is elevation above the bed, the flow velocity profile is going to go to 0 at the z naught. Typically that z naught is very tiny, and then is going to build up and eventually look something like this. And so what you can see is that that's very, very different. So this is law of the wall. That's very, very different from what we had earlier when we just had this kind of straight linear velocity profile. So this is just going to be our linear viscous. And you might notice that there's a big depth in which velocities are very similar. So law of the wall, velocities similar across broad depth range. And what's the reason for this? This gets back to what we've been talking about this whole time. It's turbulent mixing. So all of the parcels of flow in the bottom of this column being pushed up towards the top of the column. So all the slow material moving up, all the fast material moving down. That's what creates the law of the wall. That's what creates this turbulent, more mixed velocity profile that we have right here. And so here we are at our final expression, and I am going to put a box around it in blue because it's super important for our understanding of water.